The sunset you're watching tonight is not the same sunset a 25-year-old is watching, not metaphorically, physically. The light reaching both of your eyes is exactly the same. The same photons, the same wavelengths, the same stream of electromagnetic radiation traveling through the same atmosphere at the same moment in time. But what happens to that light once it reaches your eye is different. Over the decades, the eye itself changes in ways that scientists can measure with surprising precision. The filters inside your eye slowly shift. The way your retina responds to color subtly evolves. Even the size of your pupil changes. The light hasn't changed. The instrument receiving it has. And when that instrument has had 60 or 70 years to evolve, something remarkable happens. In certain moments, especially during sunset, the older eye can actually see the sky in a richer, warmer way than a younger one. To understand why, we have to start with the light itself. The light you see at sunset isn't actually sunlight. When you look at a sunset, you are not seeing the sun's original light. You are seeing what remains of it. Sunlight, when it leaves the surface of the sun, is essentially white. That white light is a mixture of all visible wavelengths, from short wavelengths like violet and blue, around 450 nanometers, to long wavelengths like red, around 700 nanometers. All those colors travel together as a single beam. But the moment that beam enters Earth's atmosphere, things start to change. The atmosphere is not empty. It is filled with billions of tiny molecules, mostly nitrogen and oxygen, suspended in the air. When sunlight collides with those molecules, the light doesn't simply pass through untouched. It scatters. And here is the key: not all wavelengths scatter equally. Short wavelengths, like blue and violet, scatter far more easily than long wavelengths like red and orange. The relationship is not linear, it is dramatic. In fact, the intensity of scattering follows a precise rule discovered in the 19th century called Rayleigh scattering. The formula shows that scattering strength is proportional to 1 divided by the wavelength raised to the 4th power. That 4th power matters enormously. Because of it, blue light around 450 nanometers scatters roughly 9 times more strongly than red light around 700 nanometers. Not twice as much, not 3 times as much, 9 times. That single mathematical relationship explains 3 everyday wonders of the sky: the why the daytime sky is blue, the why sunsets glow orange and red, why the color of the sky changes minute by minute as the sun sinks toward the horizon during the middle of the day. When the sun is high overhead, sunlight passes through a relatively thin layer of atmosphere. Blue wavelengths scatter outward in every direction, filling the sky above you with blue light. That scattered blue light reaches your eyes from every part of the sky. That is why the sky appears blue. The sun itself looks slightly yellow during the day because some of its blue wavelengths have already been scattered away before the beam reaches you. But the effect is mild because the sunlight hasn't traveled very far through the atmosphere. At sunset, everything changes. Why sunsets turn red? As the sun moves toward the horizon, the angle of sunlight entering the atmosphere becomes extremely shallow. Instead of passing through a short vertical column of air, the sunlight must now travel sideways through a massive stretch of atmosphere before reaching your eyes. In this geometry, the light can pass through 10 to 40 times more atmosphere than it does at noon. Every additional mile of air becomes another battlefield where molecules scatter away shorter wavelengths. Blue light disappears first, then much of the green. By the time the beam finally reaches you, the surviving light is dominated by the longest wavelengths: orange, red, and deep crimson. The atmosphere hasn't added color to the sunlight. It has subtracted it. A sunset is not the sky painting itself. It is the sky removing colors until only the warmest ones remain. This is why a sunset sky is never a single flat color. Look closely, and you will always see a gradient. Near the horizon, where sunlight has traveled through the greatest thickness of air, the colors become deep reds and oranges. Higher in the sky, where the light has traveled a shorter path, some yellows remain. Higher still, near the top of the sky, blue still survives because the path through the atmosphere is shorter. A sunset sky is essentially a map of atmospheric distance, painted in the colors that survived the journey. Sometimes the atmosphere adds another twist. After major volcanic eruptions, sunsets around the world can become extraordinarily vivid. When volcanoes like Krakatoa in 1883 or Mount Pinatubo in 1991 erupt, they inject massive amounts of ash and sulfur dioxide high into the stratosphere. These particles create a second type of light scattering called mice scattering, which behaves differently from the molecular scattering of air. These larger particles scatter certain wavelengths more strongly and can push the surviving light even further toward reds and purples. After Krakatoa erupted, sunsets across Europe became so intensely red that fire departments reportedly received emergency calls from people who thought entire cities were burning on the horizon. The sky looked like it was on fire, but it was just physics. The light reaches your eye, but your eye is not the same. Now we arrive at the second part of the story. Once the sunset light finally reaches your eye, it must pass through a series of biological filters before it becomes something you actually see. The first of those filters is the lens of your eye. Inside every human eye sits a transparent structure called the crystalline lens. It is located just behind the iris and pupil, and its job is to focus incoming light onto the retina at the back of the eye. In a young person, this lens is nearly perfectly clear, but it does not stay that way forever. Over decades, something subtle happens. Sunlight contains ultraviolet radiation, and that UV light slowly triggers chemical reactions inside the proteins that make up the lens. These proteins, called crystallins, begin to accumulate pigment molecules over time. One group of these molecules, known as 3-hydroxyquinureinine derivatives, gradually builds up within the lens. The result is something ophthalmologists can clearly observe during eye exams. The lens slowly turns yellow. At first, the change is almost invisible. By the time someone reaches their 60s, however, the yellow tint is easily detectable with medical instruments. By the mid-70s, many lenses have developed a noticeable amber color. One of the first scientists to study this process systematically was a British vision researcher named Robert Wheel. In the 1960s, he began measuring exactly how the optical components of the eye change with age. His work revealed something fascinating. The lens does not simply become cloudy, it becomes a selective filter, and that filter is very specific about which colors it absorbs. Measurements show that by age 70, the human lens transmits roughly 50% less blue light than the lens of a 25-year-old. Half of the blue wavelengths that would normally reach the retina are absorbed before they even get that far. In everyday life, this has certain drawbacks. Older adults sometimes find it harder to distinguish subtle differences between blues, such as navy versus black. Colors across the whole visual field become slightly warmer, although most people don't notice because the brain constantly adjusts its internal white balance. But this yellowing lens also performs an unexpected service. It protects the retina. Your aging lens is also a shield. Blue and violet wavelengths carry more energy than red wavelengths. When these high-energy photons strike the retina, they can produce reactive oxygen molecules that damage the cells supporting your photoreceptors. Over many years, that damage contributes to age-related macular degeneration, one of the leading causes of vision loss in older adults. The yellow pigments accumulating in the lens absorb precisely the wavelengths most responsible for this damage. In other words, the same pigment that changes the color of the world is also acting like built-in protective sunglasses for the most delicate part of your eye. Your lens has quietly been protecting your retina for decades. And at sunset, this change creates a fascinating optical side effect. Because the atmosphere has already removed much of the blue light before the beam reaches you, and your yellowed lens removes even more of the blue that remains. The light reaching your retina has effectively passed through two warm filters. First the atmosphere, then your lens. The reds and oranges pass through both filters almost untouched. The result is that the image forming on your retina contains a higher ratio of warm colors than the same sunset reaching a younger eye. Your aging lens is doing something photographers intentionally do with their cameras. It acts like a warming filter, except yours developed slowly over decades without you ever realizing it.